Here's a tutorial on how to sketch the curve y equals x times e to the negative x, using calculus, so just using analytic information. Alright, we are going to hop right into it. We're going to first start to think about this thing in terms of just general properties of function. So let's think about what its domain is. So are there any weird things, values of x, that make this thing undefined? And there's no domain restrictions for this, there's no domain restrictions for this, because there's no domain restrictions for what you put into an exponent of an exponential. So because we're all good here, there's no x values that are restricted from here. Alrighty. Second thing is we want to find intercepts. So to find y-intercepts, we're going to substitute in x is 0, so we get 0 times e to the negative 0. So this ends up being 0 times 1, which is still 0. So we have a y-intercept at 0, 0. For x-intercepts, we will set this thing equal to 0. And the only way a product of two things can equal 0 is if either the first term is equal to 0 or the second term is equal to 0. That's if there's only two things. Well, this gives us one value, and this thing has no solution, because an exponential, constant in the base, and some sort of function up in the exponent is never equal to 0. This thing looks like this, just as like a graphical demonstration. It looks like that. And there's an asymptote here, and this function, this guy right here, is never equal to 0. So this thing has no solution, meaning our only x-intercept is also the y-intercept at 0, 0. Okay, so 0, 0 is the only intercept we have for this entire function. Alright, now let's actually get to some calculus. So we're going to take the derivative of this thing. This is a product, so we're going to have to use the product rule. So the derivative of the first thing is just 1 times e to the negative x. We're going to add to that x times the derivative of this thing. The derivative of this would be, because it's an exponential with a base of e, would be the same thing, but then we have to multiply by the derivative of this. That's the chain rule coming into play. Alright, let's clean that up a little bit. This ends up being e to the negative x. I'm going to put this negative in front here and call this minus x e to the negative x. And there's our derivative. We can actually factor this, which will make things later a little bit easier. Take out the e to the negative x, and this becomes 1 minus x. Okay, so there's our derivative. Now, in order to find information about increasing, decreasing intervals and maxes and mins, we have to set the derivative equal to 0 or find where it doesn't exist. So either y prime is equal to 0 or y prime does not exist. Well, there's no domain restriction for this function. I can plug anything I want in for x up here, anything for x right there, and this is fine, so there's nothing that makes this not exist. But if we set this equal to 0 and solve, we will get some stuff. So again, product of two things, this times this equals 0. Either this is equal to 0, which we've already discussed above, cannot happen, or 1 minus x equals 0. This we can solve by adding x to both sides. 1 is equal to x. Alright, so what that means is we have a value of x that makes the derivative equal to 0. What we then do is we take both of these, all of these values, of course there's only one, put it on a number line, and we sign test the derivative. So if we were to plug something less than 1 into the derivative, would it be positive or negative? Well, this thing's an exponential. Again, the graph of it's right here. It's always positive. So this thing is always going to be positive regardless of what x is. This, however, if we plug something less than 1 in, 1 minus something less than 1 will be positive. So this will be positive. If we plug something greater than 1 in, like 2, again, always positive. 1 minus 2 is negative. So we end up getting a negative for the whole derivative. All right, so this tells us two pieces of information. One, that we have intervals of increase and decrease here, so it is increasing on the first interval, negative infinity to 1, and it is decreasing on the second interval, 1 to infinity. Also, that at 1 it looks like there's a max, and if we plug 1 into the original function, we'll get the full point. So the max is at 1, comma, and if we plug 1 into the original function, we get 1 times e to the negative 1, which is just 1 over e. Okay, so there's our maximum. We're going to put this right there because that becomes important. Okay, cool beans. Now what we're going to do is take the second derivative. I'm actually going to use this form of it. So I'm gonna use this. So y double prime is equal to, this is a product, so I'm going to use product rule. First I'm going to take the derivative of this one, so that would be e to the negative x times negative 1 multiplied by 1 minus x, plus, now this stays the same, e to the negative x, and we take the derivative of this, which is just 0 minus 1, so negative 1. Cool. Alright, actually both of these terms have two things in common. They have an e to the negative x and they have a negative 1. So I'm going to factor that out. Take out the negative 1, e to the negative x, and what's left over is 1 minus x plus 1. And to clean that up, I'm going to call this negative e to the negative x. Combine the 1 and the 1, make it 2. 2 minus x. Okay. Go through the same process we did over here. What makes the second derivative either equal to 0 or what makes the second derivative not exist? Once again, this is unrestricted. You can plug anything you want in for x here. You can substitute anything you want in for x here. You get no domain restrictions here, so there's nothing that makes the second derivative not exist. However, if we set this equal to 0, once again we will be able to solve for some stuff. Either negative e to the negative x is equal to 0 or 2 minus x equals 0. We know this isn't going to yield any results. This, however, will get 2 is equal to x. So there is the critical value for the first derivative, and it gives us a value in the second derivative to test. Okay, so we're going to test this out. Here we go. If we plug something bigger than 2 in, this will end up always being negative. And I'll do something less than 2, so like 1. This will end up being negative. It'll be negative 1 over e. This will be positive. A negative times a positive is negative. If we plug something bigger than 2 in, like 3, this will still be negative. It'll be negative 1 over e cubed. This will end up being negative as well, and a negative times a negative gives me a positive. Okay, so that tells me that because the second derivative is negative here, this curve is concave down from negative infinity to 2, and this curve is concave up from 2 to infinity. Okay, and also the point 2 comma something is an inflection point. Let's figure out what that y coordinate would be. If we plug 2 into the original function, it would be 2 times e to the negative 2, or we can change that into 2 divided by e squared is what that would end up being. Okay. What I'm going to do now is actually take these two sign charts right here. I'm going to create one giant one. Okay. I'm going to stop it at 1, stop it at 2, and let's write this information. So all the way up to 1 is increasing. So this is increasing. And anything after 1 is decreasing. So it's decreasing on this interval, it's decreasing on this interval. Okay, because of the second derivative, anything up to 2 is concave down. So this is concave down, this is concave down, and then anything beyond 2 is concave up. Okay, alrighty, that's going to be kind of nice to help us graph. So now we're going to create a sketch of this thing. So here's our perfectly vertical y-axis and a nicely horizontal x-axis. We had, I believe, an intercept at 0, 0. Just to verify that. Yes, we had an x and a y-intercept at 0, 0. So we're going to mark that thing. So boom, there's our point right there. We have a point at 1 comma 1 over e. That's our maximum. So 1 comma 1 over e. We'll call that 1 comma 1 over e. We have an inflection point at 2 comma 2 over e squared, which is height-wise smaller than this. All right, so at 2 comma 2 over e, we'll just call that 2 comma 2 over e squared. Boom. And now we just create the sketch based off of the information that we gathered. Another piece of information that actually might be helpful is, I'm leaving these little weird things everywhere. Is what the end behavior is. So if we were to go up here, did we ever talk about end behavior? I don't think we did. Alright, let's quickly talk about what happens as x goes to positive and or negative infinity. Alright, so if x is going to infinity, this thing's getting infinitely big, and this thing's also getting infinitely big. You can kind of think of it like this, x over e to the x. Okay, and as this thing goes up to infinity, this numerator is growing, but this denominator is growing so much faster that we have a fraction where the denominator keeps getting bigger and bigger and bigger, and the numerator can't catch up. If you think of fractions where the denominator is getting bigger and the numerator can't catch up, they're just getting smaller and smaller and smaller and getting closer to 0. So as x approaches infinity, y approaches 0. Okay, as x approaches negative infinity, this is a negative number that's infinitely huge. This thing would be e to a negative infinitely huge number, and because of that negative exponent, it would come up into the numerator here. Or you can think of just plugging in a negative number here. You'd have a negative negative, which makes this positive. So you have a negative huge number, and then you have a positive huge number multiplied together. The result will be negative, and it'll be infinitely big. So you end up getting something that looks like that. So that tells us at the far left side of our graph, it's going down to negative infinity. So this is going to be going down to negative infinity. And then in the far right side of our graph, we have a horizontal asymptote at y equals 0. So let's sketch that horizontal asymptote at y equals 0. Okay. Okay, so the first interval is from 0 to 1, or negative infinity to 1 rather. It's increasing and it's concave down. We know that this should be going to infinity, but now we know that it's increasing, meaning it's going up, and it's concave down, which means it kind of hugs the space underneath it. Okay, so it's going to look something like this. There it is. From up to 1. Sorry, I don't know why I stopped at 0. There we go. From 1 to 2, which is just this little interval right here, it is decreasing, still concave down. So it's going to look something like that. Right? Decreasing and concave down. It's kind of hugging the area below. And then from 2 onwards, it's decreasing, meaning it's still getting lower. And again, we have a horizontal asymptote here, so it's going to approach that horizontal asymptote. But it's concave up, so it's going to kind of hug the air above it. So it's going to look something like that. And that's our sketch. Which actually, if you go on Desmos and you compare this to the sketch on Desmos, it looks pretty good. Alrighty? So that's how you get through the sketch of the graph of y equals x times e to the negative x.